Okay, so this is a situation of exponential growth, but I want you to see a situation of exponential decay. Okay, that's a typical case with endangered species. Okay, especies en peligro de extinción. So if we say there are 50 individuals of Sumatran rhino and the population decreases by 5% each year. Okay, so this would be the general term for this sequence. The original amount, let me copy this. So the original amount is 50 individuals, and if it's decreasing by 5% each year, it means that that population is multiplied by 0.95 each year. Okay, so if I compute this, of course, a sub 1, as we already know, a sub 1 is going to be, this is going to be a 1, so this exponent becomes a 0. If that exponent is a 0, all of this becomes a 1, so it disappears. Okay, what happens if I want to find, for instance, a sub 5? A sub 5, this n becomes a 5, so this exponent is a 4, so let's just make 0.95 raised to the power of 4, which gives me this value times 50, so 40 times 72. 40 times 72 is the amount of rhinos after 4 years. Okay, if they keep decreasing by 5% per year, after, like, on the 5th year, so 4 years from now, there will be approximately 40.72. Okay, we would round it to 41 because it's a number of individuals, but as an approximation, yeah, like 40 times 72 is the estimated quantity. Okay, and following the same pattern, we can find the amount of rhinos on the 10th year, 31.51, on the 20th year, 18.87. This one is wrong, so a sub 50, let's compute it again. So 0.95 raised to the power of 49 times 50, that gives me 4.05. Okay, and I have the graph somewhere here. I think it's this one. Yes. Okay, and this is that other sequence. Okay, I started here with 50 individuals, and the amount of individuals is decreasing each year by 50%. And that pattern is describing an exponential decay. Instead of an exponential growth, an exponential decay. Okay, actually, I'm going to take this and I'm going to put it here. So you have this image in the document. Okay, so once we know this, we can say, that's what I wrote here at the beginning and I erased that. If R, the ratio, if it's higher than 1, we have a case of exponential growth, which is the case of the COVID-19 spread. If R is smaller than 1, we have a case of exponential decay, which is the case of the endangered species or extinction of species. Okay, so R larger than 1, exponential growth; R smaller than 1, exponential decay. If R is just 1, we would be multiplying by 1 all the time, so we will just have flat line. So that's no longer an exponential pattern. So that's why we don't consider r equals 1, because that's not an a case of exponential growth or decay. It's not a geometric sequence is if r equals 1. So I'm going to stop recording here.